Hello everyone, continue the atom chapter. So in this session we'll study about the line spectra of hydrogen atom. So before studying the today's session about the line spectra of hydrogen atom, so let us have the brief revision of the last session, whatever we studied. So in the last session we studied the expression for energy of an electron in an orbit of hydrogen atom. So we got the final expression for energy of an electron in an orbit of hydrogen atom as En is equal to minus 13.6 divided by N square electron volt. So this is what we got the expression for the total energy of an electron in an orbit of hydrogen atom. So the negative sign indicates that the electron and the nucleus, they form an attractive system that is called as a bound system. The electron is bound to the nucleus. So as N has a discrete value, so energy of an electron in hydrogen atom, so that is quantized. So called as Bose energy quantization. So similarly we studied the expression for a frequency. So we got one relation. Frequency is inversely proportional to cube of the principal quantum number. So here N is said to be the principal quantum number. So if I consider N equal to 1 for the first orbit of hydrogen atom, the number of revolutions made per second by the electron, that is frequency of electron, is found out to be, it is 6.57 into 10 raised to 5 revolutions per second. Also we studied the energy levels of hydrogen atom. So using the total energy expression as mentioned above. So as the principal quantum number N increases, the energy levels or the energy states, they will come closer and closer to each other because the energy difference between the successive energy levels decreases with the increase in the principal quantum number. So for N equal to 1, so using the total energy expression, so that is said to be the ground state for the minimum value of your total energy. So that is E1 is equal to minus 13.6 electron volt. So this state is said to be the ground state of hydrogen atom. So N equal to 2 is considered to be the first excited state with the respective energy value. So we mentioned in the last video. So go through the last video. So you'll get the energy values. So similarly N equal to 3, so this is called the second excited state energy of hydrogen atom. So as I mentioned, N goes on increases, the energy levels or the energy states come closer and closer to each other. So because of the energy difference between the successive energy levels decreases. So as I mentioned, with the increase in the principal quantum number. So this is what we studied in my last session. So in today's session, we'll study about the line spectra of hydrogen atom. So we studied the Bose postulate. So in the while studying the Bose postulate, we have the third postulate. So energy is radiated in the form of a photon when the electron of an excited hydrogen atom, so when it returns from higher energy state to the lower energy state, one photon is emitted. So in other words, we can say that energy is radiated in the form of a photon when electron in hydrogen atom jumps from higher energy orbit to its lower energy orbit. So we can consider this as N equal to Ni, similarly N equal to Nf, initial and the final states with the condition Ni is greater than Nf. The energy of the emitted photon is given by the expression. So E equal to h nu. So directly we will consider h nu equal to the energy difference between the two energy levels. So E n I minus E n f. So using this expression we will derive the expression for wave number, also the wavelength, that is lambda. So we studied the expression for total energy for its nth orbit, that is n is equal to minus m e raised to 4 divided by 8h square epsilon naught square into n square. Using this total energy expression, so let us substitute that in the photon energy expression. So by taking initial and the final energies levels, so we'll get the expression for this as h nu is equal to m e raised to 4 divided by 8 epsilon naught square. So now we'll consider for the initial. So now it is ni square into h square minus of we'll write that equation one more time. So therefore m e raised to 4 divided by 8 epsilon naught square ni square into h square minus of here it is first one minus, here minus of minus m e raised to 4 divided by, again the same terms but for the final state nf, 8 epsilon naught square nf square h square. You go through the total energy expression, so you'll get the idea. So now I'll write the direct expression. So therefore we'll get mu is equal to h nu is equal to, by taking some of the terms here common, so that is m e raised to 4 divided by 8 epsilon naught square h cube into bracket 1 divided by nf square minus 1 divided by ni square. So now write the expression for, so now this expression is only for mu, so this is not there, and there is this. So now this constant is said to be with the value of c, Rydberg constant. So that is by taking mu equal to c by lambda. So therefore instead of mu, substitute the value of mu by c, mu by lambda. Mu by lambda is equal to m e raised to 4 into 8 epsilon naught square h cube 1 divided by NF square minus 1 divided by Ni square. So now get the value for only 1 by lambda. So I'll make here only by using this. So therefore 1 by lambda is equal to m e raised to 4 8 epsilon naught square h cube into c 1 divided by n square minus 1 divided by ni square. So now this term is constant. The value of that is said to be the Rydberg constant. So r times of 1 divided by ns square minus 1 divided by ni square. So I mentioned in my last video the value of Rydberg constant is 1.097 into 10 raised to 7 per meter. So this is said to be the expression for the wavelength of the spectral series. So R is said to be the Rydberg constant, lambda is the wavelength of the spectral line emitted. So also we can find the wave number. So 1 by lambda can be considered as mu bar or wave number. So directly 1 by lambda is replaced by mu bar. So therefore wave number can be determined using the expression mu bar is equal to r times of 1 divided by nf square minus 1 divided by ni square. So this is all about how we can write the wavelength expression, also the wave number expression using the total energy expression for the line spectra of hydrogen atom. So wave number means it is the number of waves in unit distances. So continue in the next video. Thank you.